Hello students, Mr. Courtney here. In this video, I'm going to be going over assigning quantum numbers. We'll talk about what are quantum numbers, how we use them. So we've previously covered Hund's rule, Pauli's exclusion principle, the Aphval principle. So we've looked at adding electrons to an atom. We looked at how they're added. So we've talked about electron configuration, orbital diagrams. We're going to take it one step further now and talk about quantum numbers. And what are quantum numbers? We've actually come across one of these quantum numbers already. And just keep in mind, when we get to it, you'll be like, ooh, oh, that's what it is. That's what that means, because you've seen it already. So the quantum numbers, there are a set of 4 numbers used to describe electrons in an atom. So it is like the address of each electron. So we've come across the principal quantum number already, n, and we'll discuss this a bit more in a few seconds or a few minutes. The azimuthal quantum number, L, magnetic quantum number, m sub L, magnetic spin number, m sub S. So you see that these numbers, what we'll see is that they're based upon the previous one. So the values of n determines which values we can have for L. The values of L determine which values we can have for L. And we'll see that. So let's go back a bit and talk about the address of an electron. So if you want to compare it to something like this. So think of the n as being the state. When you give someone, you give the state. L, like it is similar to something like your zip code. Then the street name. So which street does that person live on? And then the house number. So it is very much similar to that. These are the things we use to identify or to find a location on when we go in somewhere. So we need to know the street, the state the person lives in, the zip code, the street name, and then the house number. So we have a very broad, we narrow it down, we narrow it even further, and then we pinpoint exactly where that person lives. So that's the same thing we're going to be doing with these quantum numbers when we're talking about the address or the location of each electron. The principal quantum number describes the energy level. We've talked about energy levels already. So this is the one we already know. And we have the symbol N for it. It is the same as Bohr orbits. We talked about the Bohr model where he stated that electrons are found in fixed orbitals around the nucleus. And we later found out that these orbitals are not fixed, okay? But instead they're in regions where we find the electrons. So they're not in fixed orbit, but we know they're in a certain region. But the fact that they're still found in levels, certain regions outside of the nucleus, that is what we talk about our energy levels. And energy levels can be positive integers, so positive whole numbers from 1 to infinity. Here we see on a diagram n is equal to 1, 2, 3, 4. So that tells us the number of energy levels. The azimuthal quantum number. This defines the shape of the orbital in 3 dimensions. So is this orbital spherical, dumbbell, as we've seen before? Okay, so that's what we're talking about. So it describes the shape. Because the orbitals have different shapes, they're going to occupy different regions. And that's what we talk about our sublevels. So we have the S sublevel, which is spherical. The L value is 0. The P sublevel, dumbbell, the L value is 1. The D, L value is 2. And the F, L value is 3. How do we get these 1, 2, and 3? L is equal to n minus 1. In the first energy level, we have the s orbital. So 1 minus 1 is 0. In the second energy level comes the p. So n minus 1. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. So that's how we get these values for L. It's n minus 1. The magnetic quantum number. This defines the orientation of the orbital, and its values can range from negative L to positive L. Let's look at this. For the s orbital, it has one possible orientation. What's the value for L for the s orbital? Remember, it's 0. What's negative 0? Still 0. What's positive 0? Still 0. So that means our s orbital has one possible orientation. The p orbital has 3 possible orientations. Remember, the L value for the p is 1. So we can have -1, 0, +1, because it ranges from negative L to positive L. Same thing with the d orbital. The L value is 2. So the m sub L value can range from -2 all the way to +2. And then when we get to the f orbital, L value is 3 for the f orbital. So the m sub L ranges from -3 to +3. So we can have 7 possible orientations. Now those numbers should ring a bell. Something should be going off in your head right now saying, oh, this makes sense. I know this. We have one possible orientation for the S. That's our one line. We have 3, 5 in the P, 7 in the F. Now what does that sound like? Remember, these are the same as our orbitals. There's 7 different orientations in the F. 5, 3, and 1. So that should ring a bell right there. Now, the magnetic spin number, the last of the 4. This indicates the spin of the electron. Spin, what does the spin mean? We talk about the orientation of the electron. We use that word, orientation. When we added the first electron, we used arrows pointing up. When we added the second electron to an orbital, we use arrows pointing down. So they have different orientations. And that is what we were using to represent our magnetic spin number. Remember, no 2 electrons in the same orbital could have the same spin or the same 4 quantum numbers, Pauli's principle. Or we talk about Hund's rule. Electrons are added, or orbitals rather, are half filled, and electrons are added with parallel spins before the orbital is filled. So the first electron added to each orbital is given a positive value, positive 1/2. The second electron is given negative 1/2. Positive, we had the arrows pointing up. Negative 1/2, we had the arrows pointing down. So we were doing it already. You just did not know you were doing it. Okay? So now we're going to fill in this orbital tree diagram. Here we're going to find our principal quantum numbers, and that is what energy levels. Here we're going to put in our sublevels, our azimuthal quantum numbers, and here our magnetic quantum numbers. So our energy levels will be 1, 2, and 3. Now what orbitals, or what sublevels rather, are found in these energy levels? In the first we have the S. In the second we have the S and the P. In the third we have the S, the P, and the D. So what are the values for L? Remember, L is equal to n minus 1. So if n is 1, our L values will be what? For the first energy level, it will be 0. 2 minus 1 is 1. 1. And 3 minus 1 is 2. So all our S's will be zeros, all our P's will be 1, and all our D's will be 2. So let's get to our magnetic quantum number. Remember, it ranges from negative L to positive L. So if we start filling these in now, all the S's will be zeros because negative 0 is still 0. So we fill in all the S's. Remember, if you need to pause or go back, that is completely fine. You do it on your own time. Okay. Now the P's range from negative L to positive L, so that's negative 1, 0, positive 1. So again here, negative 1, 0, positive 1. The D's will go from negative 2 all the way to positive 2, because it goes from negative L to positive L. So this one here now, we're going to the 4th energy level, and you should be able to fill this out on your own. So here's what you can do now. Pause the video, fill it out. Remember, use pencil. So if you made a mistake, you can go back and correct it. So again, pause the video, and then you can come back and see the answers. Alright, so there you go. Here are your solutions to the magnetic, not the magnetic, but the quantum numbers for the 4th energy level. Okay? Okay, so let's go ahead and fill out this video now. This table. Now, you should be able to do this table on your own. Okay, remember, what are the different sublevels we have? We have the S, the P, the D, and the F. How many orbitals are in each one? We have 1, 3, 5, and 7. With 2 electrons in each orbital, we have 2, 6, 10, and 14 maximum. In terms of our energy levels, 1, 2, 3, and 4. In the first energy level, we only have the S, so we have 1 orbital, 1 sublevel, sorry. In the second energy level, we have S and the P, so we have 2. In the third, we have the S, and that's not an S. So we have the S, the P, and the D, so we have 3. And in the fourth, we have a S, the P, the D, and then F, so we have 4. Now you notice you're given for any energy level N, there can be at most how many sublevels? Compare the values of N to the number of sublevels. They are the same, so that means there can be N sublevels also. The number of orbitals. And how do we get the number of orbitals? Well, we have the S. The S can only have 1. So how many orbitals do we have here? 1. We have an S and a P. So add the total from the S and the P, which is 3 plus 1. So that will give us 4. Okay, let's do the same thing. In the third energy level, we have the S, the P, and the D. We already know the S and the P together gives us 4. So add the 5 from the D. That gives us 9. So add the 7 from the F to the 9 from the S, the P, and the D. That gives us 16. So what did we do? Sorry. What did we do to N to get the number of orbitals? 1 to 1, 2 to 4, 3 to 9, 4 to 16. So here we'd see that we squared the number of energy levels to get the number of orbitals. So here would be N squared. And we already said to get our maximum number of electrons, we already said there are 2 electrons per orbital. So all we do now is multiply the number of orbitals by 2, and that gives us the maximum number of electrons. So that would give us 2, 8, 18, and 32. And since we multiplied this by 2, this is N squared times 2. So this is 2N squared. Now, if you compare this to the orbital tree diagram that you just did, you'll see that these here would match up, and then just multiply by 2 and we'll get the number of electrons in each orbital. Alright, so let's see how we can use these quantum numbers to tell the position, or the address as we said, of electrons. So the first quantum number we studied was the principal quantum number, N. Okay, remember it tells us the different energy level, which energy level we on. So everything here will be 1, 2, 3, 4, 5, 6, 7. Okay, but remember when we get to these here, this will be a bit different. What do you think these numbers for our D block elements, what are they going to be? Where do they show up first? So go back. Where do they show up first in the periodic table? What is it? These here will be 3. So all these will be 3. These will be 4, n minus 2. And this will be 5, n minus 2. Okay, so that's our principal quantum number. Now our magnetic, sorry, not magnetic yet, azimuthal quantum number, L. Everything in the S sublevel we said is 0. So our values here will be 0, 0, 0, 0. And remember, this one here is actually in the first energy level, so it would be S, so it would be 0. But the P's will be 1, 1, 1, 1, 1, 1. What will the D's be? 2's, 2, 2, 2, 2, 2, 2, all the way across. The L, when we get to lanthanide and actinide series, they're in the F block, so they're going to be, all these will be 3's. Okay, and you can fill all those in on the chart, the empty chart that you have. Okay, now let's get to our magnetic quantum number. And we said for the S sublevel, it's also going to be 0. And I hope you can see this clearly. 0, 0, 0. Now let's get to the P's. For the P's, it is different because the first electron, remember the value ranges from -1 to +1. So we start, the first electron gets -1. I don't think this color is working good. Let me change the color. Okay, so let's use a different color here. Let's see this. So let's see if we can erase this. And we start with -1, 0, +1. Then we start back at -1, 0, +1. Okay, again, so it's -1, first electron in the orbital. First electron in the next orbital will be 0. First electron in the third orbital will be +1. And then we start back again at -1, 0, and +1. When we get to our D block, and I'll just erase this here so we can remember. In the D block, remember we start at -2, -1, 0, +1, +2. Then we start back -2, sorry, -1, 0, +1, +2. So that tells us all the elements here, all the electrons found here, will have a magnetic quantum number of 0. All the electrons found in this column will have a magnetic quantum number of -2. Those here will be -1, 0, +1, +2, and you can follow as we go along here. Okay? What would it be for those here in the F block? So in the F block, we'll start at -3, -2, -1, 0, +1, +2, +3. And then you continue again from your -3, -2, -1, sorry, 0, +1, +2, and +3. So that is our M sub L. Now, the last one we're going to add are a magnetic spin. Alright, remember the spin M sub S. Okay, so M sub S, what do we use for M sub S? So we just use M sub S. M sub S is just +1/2 or -1/2. So the first electron added to the orbital is given the spin number of +1/2. The second one is given -1/2. So that's how we do it. Now when we get to these here, it's a bit different to get to the P's, the D's, and the F. we have to do it a bit different again. So I'm just gonna put these at the top there now. So now they're gonna be what? Let's start with the p's. In the p's, we're gonna go positive 1/2, first electron, positive 1/2, positive 1/2. So why are the first three positive 1/2s? Because remember, in the p we have 3 orbitals, so each, and we have to half fill. So each of these will be the first electrons in there, in each orbital. Then we get to the second ones would be negative 1/2, negative 1/2, and also negative 1/2. So what does that tell us when we get to the D's now? Positive 1/2. How many orbitals do we have? 5. So we have to half fill 5. So the first 5 will have positive 1/2. So first 5 will be 1, 2, 3, 4, 5. All these will be positive 1/2. These 5 will be negative 1/2. When we get to the F's, these 7, did I get to 7? Here, sorry. These 7 will be positive 1/2, and these 7 will be negative 1/2. So that's for the spin number. Okay. So there you have it. And you can fill out your periodic table and see how it looks. So in this diagram here, it basically sums up what we just talked about. It gives you a different perspective of looking at it. Our magnetic quantum numbers, our L values, our azimuthal quantum numbers, magnetic quantum numbers, and our magnetic spin. So that's for everything in the S. That's what the P's will look like. That's what the D's will look like. And that's what the F's will look like. Okay? Okay, so let's go through 2 examples of how we can use these. We can use these to find the last electron, or we can use that to find the element. So in the first one, we're going to assign quantum numbers to the last electron placed in carbon. So we need to first find carbon on the periodic table. So that's element. Carbon has an atomic number of 6, so that's 1. Remember, helium is missing here. So that's 1, 2, 3, 4, 5, 6. So we know that it's found in the second energy level. So that means N will be equal to 2. We know it's in the P block. So the L value is going to be 1. So our L value is 1. We need to find its magnetic quantum number. Okay, so it's here. So it is 0. That's our magnetic quantum number here. 0. Now we need to find our magnetic spin number. It's just in the first 3 in the P block, so it's the first electron added to the second orbital. It's going to have a positive spin number. So that's positive 1/2. So this is how we do this. Now, on the opposite way, we're going to use the quantum numbers to find which element's last electron could the following set of quantum numbers belong to. So we have this set of quantum numbers here: 3, 1, 1, positive 1/2. So if we start with N is equal to 3, we know we're in the third energy level. So I'll go ahead and highlight the whole thing. So we can be here or here. Good. Now, L is 1. Where is L equal to 1? L is equal to 1 is in the P. So we know that this is not true. So we don't want here. So we don't want this. I'm just crossing this out to show you how I go about doing it. Now the M sub L value, okay, our magnetic quantum number is 1. So we look here and see which of those are 1. Can't be here, can't be here, can't be here, and it can't be here. So it's either of these 2 elements. So it can either be, we said, these 2 elements, phosphorus or argon. Then we look at the last one, the magnetic spin number. When we look at the magnetic spin number, we realize it's positive. So it cannot be argon. It has to be here. And that is phosphorus. So that's how we go about doing that. So here, remember when we talked about Pauli's exclusion principle, no two electrons in the same orbital can have the same 4 quantum numbers. So here we have it. These 2 electrons are found in the same orbital. They have the first 3 quantum numbers being the same, but the last quantum number, the magnetic spin number, the magnetic spin is different. So that's how we come up with Pauli's exclusion principle. That's a way of seeing, rather, Pauli's exclusion principle. Alright, so we've come to the end of this video. So we've looked at quantum numbers. Remember, we have 4 of them. The principal quantum number N, azimuthal quantum number L, magnetic quantum number M sub L, or magnetic spin M sub S, and we use those to determine the location of electrons in an atom, and it actually defines the position of the last electron that's been added to an atom. Alright, as usual, you can review this video as many times as you want to, and I hope this was very helpful to you guys, especially for those who missed class. Until the next time, I'm out. Bless.